Scientists are often confronted with numbers that look like this. Can you guess what weighs this much? It's even hard to guess how to even say this number, let alone think about what weighs this much. I mean, if it were just 2 zeros, we would have 300. Or adding 5 zeros, 300,000, 300 million, 300 billion, 300 trillion. But there are a total of 53 zeros. That's an extremely large amount of weight, of kilograms. So we need an easier way of saying and writing this number. Can you match these big objects to their weights? So here we have, again, 1, 2, 3, 4, 5 extremely large weights, and we're trying to compare them and match them with our objects in our universe and our world. You have to think about the relationships of the quantities to each other. You have to think what these numbers mean to you before even looking at the objects, and what the objects mean to you and their weights, and what properties we can use to help us. Here we have the Earth would be this weight. The Great Pyramid at Giza would be this weight. The blue whale, which is the largest animal on Earth, would be this weight. The total human population would be this weight. And the sun would have this weight. As you can see, the sun is our heaviest object here from our big objects. And the whale, even though the biggest mammal or animal on Earth, is actually the smallest or lightest weight out of these objects. We can also do this matching with really, really small objects and their weight. Here, objects like a grain of sand, a molecule or steam, although very light, still has a kilogram measurement. And it would be a decimal because it's very, very small. See if you can now match thinking of our same question. What's the relationships of the quantities to each other? What do these numbers mean to you? And what do these objects mean to you before trying to match? And then thinking of the properties you can use to match them. So here, a grain of sand would be this weight. A molecule would be this weight, and steam would be this weight. So here, a molecule would be the lightest, and steam would actually be the heaviest. These examples were written in standard form, which is the form we normally use. Standard form is a number whose scientific form has been expanded, and is our most familiar form of a number. It's not the correct form, but it's our most recognizable, and we often compare it to other forms. And it's just numbers you've seen, like 4,500,000, a decimal 0.006789. It's very familiar to us. We work with them all the time. It's the form we normally use. But this standard form is difficult to work with when a number is huge or tiny, if it has a lot of zeros. So scientists have come up with a more convenient method to write very, very large and very, very small numbers. So this is called scientific notation, and it doesn't change the value of a number. Scientific notation is a convenient system that scientists developed to write big or small numbers, and it uses power of 10 that does not change the value. We're going to see it has a certain format, and it's helpful for really, really big numbers and really, really small numbers. We're going to see how we can convert between the two and how we can perform some operations with them as well. Scientific notation uses powers of 10 to write the big or small numbers more conveniently. Now remember, a power is a number that shows you how many times to use the number in multiplication. It's a quick way to write the repeated multiplication. So two different words you might be more familiar with are exponents or index. So for example, 10 to the power of 3. You have a 3 means it's going to multiply 3 times, and it's going to be a key role in our scientific notation. Using scientific notation requires us to also use the rules of our exponents or powers that we've learned earlier. And while we develop those rules for all different bases, we only use a base of 10. Now remember, the base is the number that is going to be raised to a power. It is multiplied the number of times shown in the power. So here the base is always the larger number, and in scientific notation we always use the 10 So here, 10 to the power of 3, the base is 10. That's the number you're multiplying however many times. Here's examples of powers of 10. We have 10 to the first, second, third, fourth, fifth, etc. You can keep going on, and it's helpful to see not only weights, but different distances. You can actually see if you go to a link, they'll show you the distance all the way from the Milky Way to Earth, to an oak tree, and then even within a cell. Powers are a quick way to write repeated multiplication, just as multiplication was a quick way to write repeated addition. So these are all equivalent. We have 10 to the third is the same as 10 times 10 times 10, which in standard form is 1,000. Again, the base is 10 and the exponent is 3. Remember that when multiplying numbers with exponents, if the bases are the same, you write the base and you add the exponent. This is key. For example, we have different bases of 2, 3, 10, and 4, but here we're multiplying the same, so we're adding the exponents. The most key example is 10 to the 8th times 10 to the negative 3. Your base is the same, so we're going to add the exponents. 8 plus negative 3 gives us a final exponent of 5.